sir.
Okey, dengar. Ni Muhammad Hadi dengan awak share komputer Muhammad Hadi eh?
Betul.
Okey. Okey, mulakan.
Assalamualaikum warahmatullahi wabarakatuh. Everyone, today our group is going to present design of machine tool structure and analysis. Morning, everyone. When we look at a machine tool, we often focus on the spindle or the CNC controller. However, from a design perspective, the structure is the most critical element. It represents between 70 to 19% of the total machine mass. My role today is to explain why we invest so much material into the skeleton of the machine and how we categorize these components based on the mechanical function. To ensure high quality parts, we must choose the right materials, whether that's traditional cast iron or modern epoxy concrete. Today, we don't just guess if a design will work. We use finite element analysis, FEA. This allows us to use computers to predict how the machine will handle heat, movement, and heavy loads before we even start manufacturing. This ensures we get the most accurate and stable design possible. This is the finite element analysis, modern necessity, and the designer's advantage. Function of machine structure. To provide rigid support on which various sub-assemblies can be mounted, such as pads and bases. To provide housing for individual units or their assemblies like gearbox, spindle head, and to support and move the workpiece and to relatively such as table carriage, tailstock, and etc. A machine tool structure must satisfy several keys to requirements. First, it needs extreme accuracy. This isn't just for day one. The geometrical accuracy must be maintained for the machine's entire service life. The structure must be stable and safe, ensuring that heat and heavy loads don't cause machine to bend or deform. Then, we need thermal control over critical parts like the spindle to ensure the parts we make are exact. Next, the machine must be fast and productive, supporting tools change and rapid movement up to 60 meters per minute. Finally, to meet all those needs, the foundation is always the same. We must choose the right materials to ensure the machine has high static and dynamic stiffness. For classification, of machine structure, we have three main classification categories. First, by purpose, beds, framework, carrying bodies, vessels, backplates, housing, boxes, column, pillar, and bracket. Hilang muka ni. Yeah. Mhm. My purpose. Mungkin tiba-tiba muka hilang. Ada. And then second, by method of manufacture. We have cast, welded, combined cast, and welded. And the third one, by function they perform. Bed and bases, board type housing in which individual units are assembled, and part to serve for supporting and moving workpiece and tool, such as table and carriage. Material for machine tool structure. First, modulus of elasticity. This measure inherent structure stiffness. High elasticity value are critical to minimize elastic deformation, undercutting loads, ensuring the machine maintains precise alignment throughout the process. Next is damping capacity. This is the material's ability to dissipate vibration energy. Height damping is essential because it suppresses through chatter and resonance, which directly determines the quality of the surface finish. Third is thermal expansion. We want low expansion to prevent what we call thermal drift. This ensures that as the machine heats up during a long shift, the tool position stays accurate and doesn't shift out of tolerance. Fourth, we have dimensional stability. This is resistant to long-term warming and creep. The structure must remain geometrically square and flat over its 15 to 20-year lifespan without shifting its shape. Fifth is the strength to weight ratio. This is crucial for moving parts like table and carriage. We need high rigidity combined with low mass to reduce inertia, allowing for faster and more accurate positioning. This is where resistant seam pads are column often act as the guideways for sliding parts. Height resistance to abrasion is essential to prevent the loss of cohesion caused by constant friction. Finally, we use specific stiffness. This is the ratio of stiffness to density. It serves as our primary benchmark to achieve the highest possible rigidity with the lowest structural mass, optimizing the overall machine efficiency. Next, we move to different material used for machine tool structure. First is cast iron. The graphite flakes inside iron just for shows. They provide natural damping and anti-friction. While it requires a long stress relief treatment, stay stable over time, it remains the most efficient choice for mass producing complex components. Next, we have mild steel weldment. Since the 1950s, steel has been favored for its high stiffness and strength. It allows us to use thinner walls, making the machine much lighter. Steel is perfect simple for heavy load structure made in small batches. However, still lacks for the damping of iron because it tends to ring. So we often use cast iron instead or hybrid welded cast designed to get the best of both worlds. Third is granite. We see granite mostly in metrology and measuring machine. Its damping is actually better than cast iron and extremely wear resistant. The threat of the difficulty in processing it, and the fact that we must monitor shock humidity, and some granite types can absorb moisture and shift out our alignment. And then finally, epoxy concrete. This is a modern mineral casting technology. It is a composite of resin and stone aggregate that offers outstanding damping. Unlike regular concrete, it is unaffected by humidity, making it a very cost-effective and stable foundation for high-precision CNC machine. So these some properties of structural material in average value. And then comparison of structural material between cast iron, steel weldment, granite, and epoxy concrete. Now we look at the design criteria for machine tool. Okay, we treat the machine tool bed as simply supported beam. Our main goal here is to find the perfect balance between strength and stiffness while using the least amount of material. So load is F, and the center of beam with length L and width P and height is H. So to find maximum normal stress, we have this equation, and this equation can be simplified as 3/2 FL, which is F is load and L is the length of the beam, and divided by BH squared. B is width and H is the height. When we calculate it, when we mathematically compare mass steel to cast iron, the results are quite striking because steel is much stronger and stiffer. It technically requires 13 times less metal than cast iron to handle the same load. This means a steel structure can be much thinner and lighter. However, in real world, we don't just design for strength. We design for stiffness. To stop a thin steel structure from vibrating, we have to add stiffening weight. It's add weight and labor back into the process. So the figure this is that while steel is more efficient on paper, we must choose our dimension based on the L squared divided by height or depth of the beam to a ratio to ensure the machine remains stable under working condition. Okay, that's all from me. So we move on to the question and answer session.
Okay, next. Next presenter. Okay. Question and answer.
Question. Boleh kan? Okay, okay.
Seorang ni present. Lagi 3 orang.
Okay, okay. Nanti macam lepas orang tu present, orang tanya soalan macam tu.
The next presenter. Sambung.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hadi bin Kalbin, and today I'm gonna present about manufacturing consideration, problem and constraints. Okay. The engineering goal is a maximum stiffness and minimum weight. When we design a machine tool, our goal is high strength and high stiffness. How do we get that? The physics is simple. Use large overall dimension with thin wall. Think of a hollow square tube versus a solid thin rod. The hollow tubes much stiffer for its weight. So as designer, we always want to push for the thinnest of wall possible to keep the machine from becoming an immovable, overweighted mountain of metal. Second, go to the process capability. Now, here is where the real work hits the drawing board. If you are chosen a cast iron, you are limited by process capability. You can just make a wall as thin as you want. Why? Because in a foundry, molten iron has to flow into a mold. If the wall is too thin, the iron might cool and solidify before it even fills the space, or the sand mold might break. Therefore, the minimum wall thickness in a cast iron is strictly detected by the size and complexity of the casting itself. Okay, and this is a recommended minimum wall thickness for cast iron structure. You can see. Next. Now we go to the economic consideration. We spend a lot of time talking about stiffness and wall thickness, but in industry, the final decision usually come down to the one thing: cost. Its name is cost. You might think a lighter steel structure is always cheaper, but it uses less metal. But that is a dangerous assumption. To make the right choice, we have to look at the comprehensive analysis, the hidden costs that don't show up on a simple material price. For metal economy, the scrap factor, let's look at economy of metal. In cast iron, if we need a hole, we use a core in the mold. The metal simply flow around it. So we use exactly the amount of iron we need. But in the welded steel structure, we often have to solid plated and machine or cut those holes out. And what does that mean? It's a mean high metal consumption. You pay for the whole plate, but 20% of it end up as scrap on the floor. Plus, you just added additional labor costs because someone or machine had to spend time cutting that hole. Finally, we have to look at the startup cost. For the casting, you have the high initial cost for pattern, the wooden or metal shape used to make the mold. For the welding, you have the cost of welding fixture to hold everything in the place while it's being joined. And for machining factor, steel is often harder to machine than cast iron, which is natural graphite and acts as lubricant. So, as design engineer, your job is to balance this. If you're making one machine, a welded steel structure might be cheaper because you don't need an expensive pattern. But if you are making 100 machine, the efficiency of casting usually win the economy race. Okay, we go to the next. All right, next, if we talk about basic design procedure. The complexity of profile designing a machine tool isn't as simple as drawing a study box. We are dealing with the highly complicated profile. Why? Because a single structure has to satisfy 5 or 6 different requirements, all at the same time. You can just design a stiffness and ignore the operator, or design for space and ignore the heat in a holistic process. So we go to the physical requirement, workpiece and space. For workpiece placement, the structure must be big enough to hold the largest workpiece the machine is rated for, while allowing the tool to travel its full range without hitting the frame. Then, space requirement. It not just empty space, we have to provide room or channel for chips to fall away so they don't clog the machine. We have also dedicated a space for hydraulic line, electrical cable, and the drive mechanism themselves. Then, next we look at external needs. For assembly and access, a machine is no good if you can fix it. We design the structure so that a technician can reach the internal part for dismantling or repair, and so the operator can work comfortably and safely. For thermal control, a machine get hot. High speed spindle and friction create heat that can make metal expand. Our design must limit thermal distortion. If the bed bend even a few micrometer because of it, the part you are making will be out of tolerance. And the final goal is a stiffness design. Finally, we bring it all together with the stiffness design. Once we know where the hook, the chips, and the motor go, we shape the dimension and remaining material to ensure the machine is rigid enough to hold its ground against the machine cutting forces generated during operation. It's about making sure the machine stays true no matter what. Next. Okay. Now we go to the 4 stiffness criteria. The static challenge is about a weight force deformation. The first thing a machine must do is support itself. Weight force deformation are static. Imagine a heavy carriage moving along a long machine bed. As that weight shifts from one end to the other, the bed can actually bow or sag slightly. Even a tiny deflection here ruin your position accuracy. We must design a structure stiff enough that its own moving part don't cause it to bend. The Next, we have cutting force deformation. These are dynamic because they depend on intensity of the work. If you are talking a deep, heavy cut into hard steel, the tool is literally trying to push the machine apart. This affects the process rate. If your machine isn't stiff enough to handle high cutting force, you have to slow down, which kill productivity. Now we enter the world of vibration. Force vibration come from outside excitation source. This could be an unbalanced motor inside the machine, a nearby forklift driving across the factory floor, or even a neighboring machine. If the structure isn't stiff and dampened, this external pulse will travel right to the cutting tool, that leaving mark on your workpiece. Finally, the most complex one is self-excited vibration, often called chatter. This isn't caused by any outside motor. It feedback loop between the tool and the workpiece. It's like stretching violin bow. The cutting process itself creates the vibration. If your machine lacks the dynamic stiffness to break, this feedback will be looped. You get a terrible surface finish and can even break your cutting tools. And as you can see, this image shows finite element analysis, or we call it FEA simulation. They visually demonstrate how the heavy weight of machine component and high pressure of the cutting tool can cause structure bending or deflection that affect precision. Okay. Then when we go to the design strategy summary. When we start a new machine to design, our primary focus is always bending stiffness. Why? Because most forces in a machine, the weight of the heavy carriage, the downward pressure of the spindle, are trying to sag or bow the structure. If your bed or column bend, even a friction of the millimeter, your tool won't hit the target. We design the overall skeleton specifically to resist this vertical horizontal bending load first. Then, once the bending is under control, We move to the secondary focus. Is a torsional stiffness. This is often the harder challenge. Machine isn't just a straight push. It involves twisting movement. Imagine a large drill bit beating into the metal. It's trying to twist the entire machine head. If the structure isn't rigid against this rotational force, the machine will ring like a wet towel. As we discussed earlier, this is where diagonal ribbing and close cross-section become your best friend. Okay. Okay. As you can see here, this diagram show how structure. This diagram show how structural element like column bed are subject to force in multiple plane. They are helpful for illustrating the bending to vertical plane and the torsional twisting. And second one is this. Okay. This simulation image show how designer check dimension for sufficient strength. The color-coded map indicate where the structure might lack stiffness or where stress highest under compound loading, allowing engineer to optimize the design for the maximum rigidity. Next. Now we talk about basic design procedure. First, we have stiffness-based design. This is the standard for the heavy hitter, like machine bed and column. In this case, shape is your king. We often have to over-dimension this because this means that if you only look at strength, the wall might only need to be 10 millimeter thick, but we make it 30 millimeter anyway. Why? Because we aren't worried about the breaking. We also focus heavily on dynamic behavior. Here assuring that the bed doesn't just hold the weight, but also absorb the vibration from the cutting process. And next is a strength-based design. This applies to component where the main goal is simply don't snap. Think of part like clamping bolt or lifting hook. While we still care that the deformation stay within allowed limit, the primary engineering calculation is to ensure the material doesn't reach its yield point. We want this part to be as light as efficient as possible, while remaining 100% safe under load. Finally, we have a combined design. This is the most challenging because you have to satisfy both criteria simultaneously. You see, this is in part like a spindle or main drive shaft. Okay, next. We go to the profile cross-sectional. In a textbook, we often study bending or torsion separately, but in a real machine tool, its compound load is our nightmare. Every column and bed is being pulled, push, bend, and twist at the same time. As designer, our challenge is how do we resist all force without making the machine weigh 50 tons. The secret isn't adding more metal. It's optimal cross-section design. Okay. Imagine you have a 10 kilogram of steel. If you're shaped into a solid, it will bend like a noodle. If you take the same 10 kg as shape into large hollow box and an I-beam, it becomes incredibly rigid. By moving the material further away from the center, which is a neural axis, we achieve an increases second movement of inertia. We haven't added a single gram of weight, but we have fundamentally changed how the part handle a load. And by choosing the shape that provided maximum moment of inertia section modulus, we achieve two things. First one is minimum deformation, the machine stay precise. Minimum stress, the material is less likely to fatigue or fail. Okay, next we go to the stiffness factor and improvement method. Okay, static stiffness ensure the machine hold the workpiece perfectly still. And dynamic stiffness ensure that when the cutter hit the metal, the machine doesn't vibrate like a turning fork. If we fail at either, we lose positioning, accuracy, and the final part end up in the scrap bin. For cross-section shape, the first and the most powerful tool in our kit is cross-section shape. As we see, the profile geometry is what determines how the load is distributed. By choosing hollow box section over a solid bar, we can gain massive amount of stiffness without adding single kilogram of weight. It's all about putting the material exactly where the stress is highest, usually as far from the center axis as possible. Next, we go to the effect of aperture and torsional stiffness. We need a hole for chip flow, access for maintenance, and space for internal gear. However, there are massive stiffness tags for this opening. While they are essential for function, they significantly compromise the structural inherent strength, especially when the machine starts to twist under torsional load. Let's look at the map of localized weakness. If you drill a circular hole with a diameter of min D, you are just weakening that one spot. The stress contraction affect a section twice the diameter in the length. Think of it as a weakness ripple in the metal. And if you cut a long slot or elongated hole, it even worse. This acts like a tear in the structure, disrupting the flow internal force much more severe than a circle. Now, here is the most important lesson for design engineer. To fit this hole, we often use cover plate. The good news about this plate provide a bending boost. They effectively restore the stiffness needed to keep the part from sagging or bowing. The bad news is they face a major torsion challenge because a bolt or screw on plate is in one with the original wall. It can stop the twisting motion effectively. It offers minimal improvement to torsional stiffness. The machine will still ring like a towel under load. Okay. All right, that's all for me. Thank you.
Next presenter.
Okay.
Test. Okay. Okay, so now I'm going to continue with effect of stiffness rates on stiffness of structure. Next. In machine tool design, having high stiffness is very important. Ensure good accuracy and high production rate. To reduce weight, engineers often use thin wall box structures, but the problem is these thin walls can be easily bent, buckle, or warp. So to solve this issue, rates and stiffness are added to improve stiffness and stability. However, it's not just about adding more stiffness. How they are arranged actually matters more. So the main intention here is to achieve a high stiffness to weight ratio for better efficiency and performance. Next. Okay. This slide shows how end cover plates affect the stiffness of a structure. Basically, end cover plates are used to close open sections in thin wall structures. By doing this, they help reduce twisting or torsional deformation. Because of that, stiffness in certain directions improves, especially in the Y and Z direction, but they don't really help much with bending. From the table, we also can see that increasing that thickness doesn't make a big difference. So the best design is when the cover plate thickness is about the same as the wall thickness. Next. Okay. This slide shows how different rib arrangement affects stiffness. Different designs give different results. Some improve bending, while others improve torsion. From the table, only certain arrangement give good improvement in both. The graph also support this, showing that better rig design leads to better stiffness. So this tells us that arrangement is very important, and among all, the diamond shaped rigs are the most effective because they distribute loads better. Next. Okay, this slide is about effect of vertical stiffness. This stiffness can be placed either inside or outside the structure, and their depth is changed to their steady effect. From the results, we can see the external stiffness are better for bending, while internal ones are slightly better torsion. Even though the difference is small, it still matters when designing for specific loading conditions. Okay, next. Okay, this one is effect of horizontal stiffness. Similar to vertical ones, but they can be replaced internally or externally, and their depth is also varied. Horizontal stiffness are very good at resisting torsion because they prevent rotation. However, they are not very effective for bending. Also, internal stiffness performs slightly better than external ones. So the best approach is to combine horizontal and vertical stiffness to get good stiffness in good bending torsion. Okay, next. Okay, the effect of fastening bolts and external vertical stiffness at bottom. First, proper bolt arrangement help improve stiffness by ensuring better load transfer and reducing movement between parts. This can improve the stiffness by around 10 to 20%. Bottom stiffness are even more effective. They reduce the effective length of the column, which lowers the deflection and can improve stiffness up to 50%. But increasing the size too much is not always good because efficiency will drop. So the design needs to be optimized in terms of stiffness, size, and bolt arrangement. Okay, next slide. Okay, for my final part, effect of fastening bolts and external vertical stiffness at bottom. Okay, they help the effective length of the structure, which reduce diffraction and increases stiffness. From the graph, we can see that stiffness increases as the base increases, but after a certain point, the improvement becomes very small. So the best design is to use an optimized size, not too small, not too big, to get a good stiffness to weight ratio. Okay, that's all from me. Okay.
Okay, next.
Okay, next. Good day, everyone. Today I will be presenting on improving stiffness of machine tool structure to the role of joint and structural analysis method. This topic is important because machine tool performance depends heavily on stiffness, stability, and proper analysis during design. So about improving stiffness, we will look at open structures such as lathe bed. Unlike closed box structures, open structures are less stiff, so we need to improve them using stiffer or ribs. According to the table, different rib arrangement can affect the stiffness vastly, as you can see in the picture. Only certain arrangement, especially arrangement 4 and 5, will improve the stiffness so much. A common design is a two parallel plate connected by a diagonal rib. The key idea of this is more ribs equals more stiffness, but also it will increase the weight and cost of the machine. So engineer will always to aim for high stiffness to weight ratio to not just maximize stiffness. Next slide. Next slide is the importance of joint. Joints connection can be vary between parts, and they play a major role in overall performance of the machine. There are two main types of joint, which is fixed joint, which is no movement, and then sliding joint that allows motion for little movement and for in the machine. From 85% to 90% of total deflection comes from joint, not the structure itself. This means even if the structure is strong, weak joint can reduce the performance and will fail in long term. Joints also will affect the stiffness, damping, and overall, the most important one I think is accuracy. So designer must ensure it is strong, rigid, and properly aligned to be used for other people. So next slide. Next is we will be talking about evaluation of machine tool structure. Now we will move to evaluate more machine structure to ensure good performance for engineers to analyze structure using two methods, which is static analysis and dynamic analysis. This will help predict any weakness such as deformation or vibration or even accuracy during the operation of the machine. There's usually the use of software such as ANSYS and etc. We will move on to static analysis. Static analysis will study force to not change with time. This includes weight of machine component, cutting force, and thermal stress. The very end goal of static analysis is to know if there is any deformation in the structure. because and then it is for displacement at key points. This is very crucial because we do not want it to fail and potentially hurt other people because of our poor analysis. So static analysis will be focused to find any deform under load use. This is important because deformation will reduce machine accuracy and even the efficiency of the machine itself, and it correlates between performance, time, and even money. And then we'll be moving on to dynamic analysis. Dynamic analysis will be studying on time-dependent behavior, especially vibration. Vibration cause a lot of tear because of the movement, so we need to look this even further using dynamic analysis. It will look on natural frequency, mode shapes, and even resistance to chatter. There are two types of force, which is external forces, which it means it will be seeing forces from cutting and rotation on the machine. And then the second main force, it is called self-induced force. This self-induced force is will be looked from the structure itself to see if there is anything wrong or any other key things that we have missed. There are certain challenges in using dynamic force, especially in terms of infinite vibration modes, and then the difficulty of damping estimation and in the parameter of changing cutting condition. So this has slight limitation, but there is other uses for dynamic analysis. And then we'll move on to the next slide. The next slide is the relation between static and dynamic analysis. In terms of definition, in terms of static analysis, it studies the behavior under constant and slow varying forces. For dynamic analysis, studies behavior under time varying or vibrating forces. In terms of type of force, for static analysis, it is for cutting forces, usually constant, and then weight, and thermal loads. For dynamic analysis, it is for more towards to harmonic forces, unbalanced rotation, and excited forces. For the main output, usually static analysis is to see the deformation in bracket displacement and stress. And for dynamic analysis, it is for more towards natural frequency and mode shapes and vibrate response. In terms of time dependency, uh, static analysis is more time dependent than dynamic analysis because it requires more process. And then for its purpose, it's usually to ensure both structural rigidity and accuracy in static analysis. And for dynamic analysis, it will prevent vibration, chatter, and instability of the machine. For complexity, it is dynamic is more complex and computational intensive. So it uses more computing power for to analyze and may require a better hardware. For static analysis, it's much more simpler to compute. So, and then for the design, the role in design, it is a first step in analysis. And then for dynamic, it's more advanced even after static study. For the key parameter, static analysis is more towards static stiffness, and then for dynamic analysis is more stiff for more dynamic stiffness and damping. Okay, next slide. We will be talking about analysis of machine tool structure. There is two main models, which is physical model and mathematical model. Physical model is an earlier method in the engineering world, and now we more use mathematical and computer methods because it is more accurate and there's more data to see. It also aims to predict real world performance in manufacturing even before we start making the project itself. So next slide. We are going to talk about model analysis. Usually in the past, engineer use scale model to make analysis. For example, a smaller model made from material like thermoplastic is made to see what we can see in our just from 3D perspective. And then we can predict the real behavior if the design is properly made. The advantages of model analysis is realistic behavior, and plus it is simple and visual to see in front of our eyes. But the disadvantage is we cannot see what is wrong with inside the model, and it's usually more time consuming and more hard to modified because it's just one physical unit that has to be made at once. So making other model with modification takes so much time, and it will take much more money and become an inconvenience. For the last part is it is not suitable for optimization. Next slide. And then we're going to talk about mathematical model. In today's engineering world, we use more mathematical model, especially finite element analysis, or in short term, FEA. This model will divide the structure into smaller elements so that we can analyze and see the crucial cons that we cannot see. It can solve equation using computers, so we don't even have to use our hand or even our brain because it is all automated into computerized software. The main benefits of mathematical model is usually because it is using computer, it is more faster to analyze and the results will be much more accurate than non-mathematical use. And then it is easy to test different design because you could design in multiple design and test at once. So that is a very good thing. However, the cons, it requires correct assumption. So the data will need to be very precise. If not you will have problems that will not be read by the computer. And the second one is usually more expensive because they need a very powerful computing power because normal laptop will not cut it because they have fewer cores and RAM to process everything. And then next slide. We're going to talk about lump constant model, or in short term, LCM. I'm going to say that this is another important method used in machine tool analysis because it simplifies a complex structure into three main things, which is masses, spring, and dampers. Instead of analyzing the entire structure continuously, we assume that mass is concentrated at specific point. Stiffness also will be represented by spring, and then we can see the energy lost by the dampers. This makes the system easier to analyze, especially for vibration and dynamic behavior. In this model, mass represents inertia, and spring represents stiffness, and damper represents energy dissipation. So basically, the machine structure behave like a mass spring damper system. This method is very useful because it simplifies complex structure and it helps estimate natural frequency. Also, it is faster than a full finite element analysis. However, it has its limitation, which is less accurate than detailed model, and it depends on correct assumption. It is not very suitable for complex geometry, and overall, the lump constant model is very quick and useful approximation method for early design stages, especially if you want to have a mock-up. Next slide. And then we're going to talk our last slide, which is finite element analysis, or in short term, FEA. It is FEA. It is a modern method used in machine tool design. FEA works by dividing complex structures into many small elements called finite element. Each element is easier to analyze, connected at points called nodes. Using this method, engineer can calculate the stress distribution, the deformation and vibration behavior of the structure. The main step in FEA are pre-processing, which is creating the geometry and mesh in software, and then solving it by applying load and boundary condition into the software itself. Plus, it has post-processing, so we could find results in matter of time. The very key advantage of FEA, it is very accurate and can handle complex shape and help optimize design before even making it in the manufacturing phase. The limitation is require high computational power and needs correct boundary condition, which which depends on the mesh quality. Overall, FEA is widely used because it allows engineers to predict performance and improve design without physical testing. In this picture is one of the few FEA examples that I could find on the internet that uses mesh and nodes for analysis. Okay, and for the conclusion, this stiffness is critical for machine tool accuracy. Rib design and joints greatly affect performance, and static and dynamic analysis are both essential in the engineering world. It relies heavily on mathematical model like FEE, but for this concept, it will help engineers improve and understand more accurate, more stable, and more efficient machine tools. That is it from me. Thank you very much.
Okay. Thank you, Group 3, for your presentation. On topic, design of machine tool structure. It's a very good presentation, all of you. Overall, very good. Seems that you prepare for this presentation. You are well prepared. Because you present not reading the text. Not the text. Very good. Now this is an example where the other group should follow lah. Okay, so that's why you need to make the preparation, practice. Don't read the slide. Read the slide is not presentation. You must explain. So you just write the point into the slide, and then the detail of the point you have to elaborate. You have to elaborate, explain. That is the way you understanding the topic. You mendalami, menghayati topik tu. Seolah apa tu, machine tu you punya. Machine tu you punya. That machine is belong to you. So that's the way you explain to people. Okay. So for the other group also, you have to prepare in order to do the best presentation. Saya dengar pun saya tak bosan. Dia punya slide pun very attractive and colourful. And dia punya dressing pun very good, very nice dressing kan. So you have to do like that. Okay, thank you. Very good. Okay, so I like this presentation. Alright, so now we open a session for question and answer. Hopefully the questioner have a question to ask, and also your pairing answer the question and also have prepared the answer. All right, so we can start. Okay, we can start question and answer. Who will be the first? Khairul Rashad.
Yes, sir.
All right, so we can start.
Okay. Assalamualaikum. Okay. I want to ask Hadi for the first question. In FEA simulations, what are we looking for to ensure the machine stay precise?
Okay. Okay. To answer your question. Sorry. Okay. For the answer is minimum deformation for deflection. We want to see that the heavy weighted cutting force don't cause the structure to bend or sag of position. That's my answer. Next.
Okay, for the second question, what is the main difference between force vibration and chatter?
Oh, okay. Nice question. For the answer is force vibration comes from outside sources like an unbalanced motor, like chatter, as I said before, self-excited is caused by the interaction between the cutting tool and the workpiece itself. Okay. Next question.
Okay, for the last question, why must a designer provide sufficient room for chips inside the structure?
All right. Next question. Okay. To prevent thermal distortion, if hot metal chip swap pile up against the structure, the heat can cause the frame to expand, or it can be bent. It can ruining the machine precision actually. Right. Thank you very much.
Okay, thank you.
Right, next questioner Nur Irfa Nadira. Okay, we'll ask the question to Rosalina. All right.
Hello. I want to ask Rushalina. First question is, why is cast iron often preferred over steel or for machine beds?
Answer for the first question, why cast iron often preferred over steel for machine beds? It is because cast iron has natural damping properties. So its graphite plate absorb vibration, which prevent the machine from shaking or ringing during heavy cutting. Next question.
Okay, for the next question, why do we use granite for high precision measuring machine instead of metal?
Okay, we use granite because granite is extremely stable. It has very low thermal expansion, meaning it doesn't grow or shrink much when the temperature changes, and it never rusts.
Okay,
Next
for
question.
the last question, what is more important for a machine tool structure, strength or stiffness?
Strength of stiffness. The answer is stiffness because while a structure must be strong enough to break, it must stiff enough to bend or deflect, because even a tiny bends ruins the accuracy of the part while being made. Thank you for the answer and thank you for the question, Ifra.
Next, Muhammad Zakwan.
Hello, Assalamualaikum. Adriana,
Yes.
I have a question. First is why are internal stiffness sometimes better than external one?
Okay. Why internal better than external ones? Okay. Internal stiffness are located closer to the core of the structure, which helps improve torsional resistance more effectively. They provide better support against twisting by stabilizing the internal section of the structure. So they can reduce deformation more efficiently under torsional loads compared to external stiffness. Yes, that's my answer for the first question. So next question.
Okay. Second is what is meant by stiffness to weight ratio?
Okay, stiffness to weight ratio refers to achieving high stiffness while using minimal material. A higher ratio means the structure is more efficient as it provides a good strength and stability without increasing weight. Ah, yes.
Okay. And last question is what happens if stiffness are poorly arranged?
Okay. If the stiffness are poorly arranged, it can lead to uneven load distribution, increased deformation, and unnecessary weight. This reduce efficiency without improving stiffness. Yes.
Thank you, Adriana.
Thank you, Zakwan.
Okay, next, Muhammad Amir Hakimi.
Assalamualaikum. I want to ask Aiman Shamsuddin. So first question is, what is the importance of stiffness to weight ratio in improving open machine tool structure?
Yeah. To improve open machine tool structure, the stiffness to weight ratio is important to determine how efficient the structure can resist the deformation while minimizing material usage. So less is good. In open structure, especially in lathe and bed, the number will increase because of the rate improvement stiffness, but also it will uh, increase in terms of weight and cost. Therefore, for optimal rig arrangement, it must be selected to achieve high stiffness with the very minimum weight. A higher stiffness to weight ratio also increase natural frequency, and also the structure will help to avoid resonance and improve dynamic performance.
Second is, why is dynamic analysis important in machine tool structure design?
It is very important because it can determine the natural frequency, mode, shape, and even resistance to vibration in the machine tool structure, and it evaluates how the structure behave under time varying force, especially during operation. It is very essential to ensure stability, accuracy, and good surface finishing.
Last one is, what is the relationship between static stiffness and dynamic stiffness in machine tool structure?
Static stiffness and dynamic stiffness are related because it can improve the static stiffness of key structural elements. Generally, it can increase dynamic stiffness as well. However, dynamic stiffness very depends on the frequency and vibration mode. So contribution of individual element may vary, but in most case, it can increase the stiffness element that dominate the static behavior and also improve in the dynamic performance in the end goal. So that is the answer from me. Thank you, Amir, for asking me.
Welcome.
Okay, guys. Congratulations to all of you. Make this presentation success. Your cooperation is very good. Okay, and so we can proceed presentation like this for the future. All right. Okay. For this group, you complete your report and include the question and answer in the report, and then submit to BLE under the folder assignment 1 before the next week, before the next class. So for our next class, 15 April, we will make the test 1. Okay, we will conduct the test 1, which this test 1 cover CLO1. Okay, CLO1, which we need to design the component or the part of the machine tools, such for example, spindle, gearbox, and so on. So we will make the test on 11 a.m. and the duration of the test is 2 hours. Okay, online at MS Team. Okay, so we prepare for the test for the next week, and for the following week, 22nd April. So the group 4 will present on the topic design of guideways and power screw. So these 4 members of this group, do your best. Please do practice for this topic. And then you can read, you can baca, and understanding the topic, and then you can explain very well. Tapi you tak baca, you tak study, kan, you nanti presentation you hanya baca teks sahaja. Jadi tunjukkan you tak faham apa pun. Kan, soalan dia dah plan kan, soal jawab dah plan. Tapi the way you present, people will know that you really understanding the topic or not. And also for the other group, which is not presenting the topic, and you also need to study for the other topics. You have to read the books, the e-books. You kena baca. Okay, the learning process is reading, presenting, calculating, and hearing. Kan? Jadi kalau you buat semua ni, you akan barulah you akan menguasai subjek itu. Menguasai maksudnya you memahami sepenuhnya lah. Kan? Belum jadi expert. Baru nak memahami, tahulah maknanya. Jadi tahu bila nak design spindle tu, contohnya bila nak design spindle, dia tahu macam mana cara nak buat. Kan? Sebab itu dah belajar. So, alright. So, for YouTube tu, you ada recording, dan ada recording yang saya record ni, you boleh take the recording ni. Saya stop dulu recording. Okay, you boleh